Hello and welcome to the Cyber1 YouTube channel. My name is Ray, and in this video we're going to talk about basic electronics and resistance. Before we can get too far into the basic electronics, we really need to understand Ohm's Law, and that's what this little table gives us. It's actually a breakdown of the various equations that we use in the calculating of other components of Ohm's Law. So with that, we can actually use Ohm's Law to calculate out all of the values on this page. So in this image we have a 10 volt battery shown, depicted here, and over here we have a 100 ohm resistor depicted here. The resistor and the battery are connected in series, so a current will flow through that resistor, and we can actually calculate out what that current's going to be. If we go back to our Ohm's Law, in this case resistance is Z, so volts divided by the resistance, so 10 divided by 100 will give us our amps. So it's 0.1 amps. At this point here across the resistor, so this is measuring the voltage across there, it's just going to be 10 volts. Having worked out what our current flowing through here is, we can now work out how much power is being dissipated or used by this resistor. In this case it's 10 volts multiplied by the amps, in this case 0.1, so 1.0 watts of power. Electricians use this as a matter of course almost every day. Things get a little bit more interesting when you start adding resistors in series. So in this case, if we add these two resistors in series, we now have 100 plus 100, which is a 200 ohm resistance between this point and this point. So when we calculate the current flowing through that 200 ohm resistance, remembering when resistors are in series you add them together, we will get a 0.05 amp power flow, or current flow I should say, flowing through these. Now the interesting thing is you can actually calculate what the voltage is in between these two resistors. If you know the current flowing through that resistor and you know its resistance, using this formula I times Z, you can calculate out the volts. So we know that the current flowing through there is 0.05 amps, and we know the resistor is 100 ohms, so that works out being 5 volts. And because these two are matched resistors, we get 5 volts down the bottom. When you sum those 2 volts together, you get your total of 10 volts coming from the battery, which is what we would expect. The interesting thing with this is we can also calculate the power on a per resistor basis and then add those together to get the total. And we can calculate these in a couple of different ways. We know the voltage across the individual resistor, and we know the current flowing through it, so we can multiply them together, and that gives us 0.25 watts. This is the same thing, but let's try and calculate it out a different way. We know the current is flowing at 0.05, and we know it's a 100 ohm resistor. So I squared, so 0.05 times 0.05, which is the same as squaring it, multiply, that gives us 0.0025 times the 100 ohms gives us 0.25. And our power total is just the sum of those two, which is 0.5 watts. When you compare it against our last circuit, we actually doubled our resistance, we halved our current, and so we halved the power that was being dissipated across the loads out of the battery. This divide or division, where we can measure the middle point between these two resistors, can be very useful. We can use that in what we call a voltage divider network. So we might have R1 and R2 joined together with a 0 to 30 volt DC input at the top, connected to a ground, and we might have a analog to digital input that takes the ground in and takes in this voltage here. But this analog input device won't allow us to put any more than 5 volts into it. So for that, we have a voltage upper limit of 5 volts. We know that our input can go as high as 30 volts. So what we need to know, we now know that we have 25 volts across there because it is the sum of these two to get to that. So what we need to do is select a pair of resistors that will keep this voltage here down to 5 volts. If we were to select R is equal to, or Z is equal to 1000 at 5 volts, we can calculate out what our current will be flowing through that. So we'll go back to our formulas. So we know our impedance is going to be 1000, we know our volts is 5, so 5 divided by 1000 is going to be 0.005. So now we know our current flowing through there. We know the same current is going to be flowing through here. So I here will be the same. And we can now calculate out what our resistance will be with a 25 volt voltage drop across our resistor. Because we're now calculating out the voltage, we'll be using this formula. So 0.05 times 25. So 0.005 times 25 volts. It's the wrong formula. I want this one. Volts divided by amps. So 25 divided by 0.005 is equal to 5000. Yep, that makes sense. So now we know that when we have 30 volts DC there, we're going to have 5 volt DC at this point. And that's the basis of a resistor network. Now, the reality is, while we can get 1k ohm resistors quite readily, the 5k ohm is not as readily available. So you would typically go with the next highest one up. Quite often that would be a 5.6 km or 5600 ohm resistor, and just make allowances for it in our program because this voltage will be slightly lower. But if you apply that 5600 ohm resistor here, you can now calculate out what the voltage drop would be here, and then we can use that with our analog input converter, depending on the number of bits it has, to convert that into a value and then into a voltage, so we can actually read what our input is. Alright, the only thing I haven't really shown you now is parallel resistors, which I haven't drawn a map for yet. But if we added another 100 ohm resistor to this one, and put that in the same circuit in parallel, you're going to get the 0.1 amp still flowing through R1, but you're also going to get another 0.1 amp flowing through R2. So that will sum up for a total of 0.2 amps. If you've got 0.2 amps flowing out of a 10 volt battery, then you must have a resistance somewhere in the order of 50 ohms, because that's what our formula is going to tell us. So if we've got 10 volts and we've got, divide that by 0.2, it's going to give us 50. So when we add resistors together in parallel, we're actually reducing our overall resistance, and there is actually a formula for that. R total over 1 is equal to 1 over R1 plus 1 over R2, etc. That's for parallel. For series resistors, it's just RT is equal to R1 plus R2, continuing on for the total number. Things get a little more complex when you have a combination of series and parallel, but you just break down each unit to give you your total for that segment and then apply it to the rest of the formula that way. That'll do for this video. I mostly wanted to cover voltage dividers. Mostly because I'm using that within Fred to monitor his battery voltages, and I did have one of my Patreons actually asked a question about how voltage dividers work. So this is actually the best description I've got at the moment for how the battery divider works, or a voltage divider works, and it's used quite a lot in industry and quite a lot in other electronic devices. If you need the input to be lower than what your receiving signal is, then you can divide it down. If you like these videos, don't forget to click on the like, subscribe, ring that notification bell so you know when other videos are released. I have a Discord channel where you can ask questions. There'll be a link to that in the description. I also have a Patreon account, and you can join my Patreons, Go Lucky, Elmorellis45, and my new Patreon, Lorenz Berger. And it was actually Lorenz who was asking about the voltage divider network. If you'd like to join them, there will be a link in the description as well. And we will see you in the next video.